all, welcome to the next video in our Week 2 series. In this video, we're going to do 3 examples of probability calculations to give you just a little bit more practice. For example 1, at a used book sale, 100 books are adult books and 160 are children's books. Of the adult books, 70 are nonfiction, while 60 of the children's books are nonfiction. If a book is selected at random, find the probability that it is fiction, not a children's nonfiction book, an adult book, or a children's nonfiction book. So when I see problems like this, where I can see 2 clearly different variables that I'm looking at, adult books versus kids books, fiction versus nonfiction, the first thing that I want to do is build a contingency table. I want to take all of those numbers that have been thrown at me and organize them in a way that my brain can process. So we're going to build a contingency table for adult versus children books and fiction versus nonfiction books. So adult versus children, nonfiction versus fiction. And you'll notice, just like all the other contingency tables we've seen, there is a total row and a total column. Next, we need to start picking numbers off of that word problem and dropping them in the table. And my instinct is let's do them in the order they were given. So it says 100 books are adult books. So here is adult, here is the total. We know that's 100. And then it says 160 are children's books. So children total is 160. And then it says of the adult books, 70 are nonfiction. So adult nonfiction is 70. And children nonfiction is 60. Now we can use what we know about this system to go back and fill in those fictions and then those fiction nonfiction totals. So 100 adult books, if 70 are nonfiction, then 30 must be fiction. And for the children's books, if we have 160 books and 60 are nonfiction, the remaining 100 must be fiction. To get the total column on the right, we're just going to add across. So 70 and 60 is 130. 30 and 100 is 130, and 130 plus 130 is 160. 260, sorry. Blech. Words are hard. So let's tackle that first question using this contingency table. I want the probability of selecting a fiction book at random. So I need the fiction total and the total. So 130 divided by 260, which is 0.5. We have a 50% chance of selecting a fiction book at random. Okay, for B, we want not a children's nonfiction. That's a weird way to word it, but children's nonfiction is easy to identify. Children nonfiction, that's the 60 box. I want to do not that. Let's use the complement rule. Not children's nonfiction should be 1 minus children's nonfiction. So 1 minus children's nonfiction, this is a little easier to calculate. We know that that should be 60 over 260. So 1 minus 60 over 260 gives us 200 over 260, or 0.7692. Remember that if you can't do fractions in your head, or you struggle with them in general, that's okay. Fractions are hard. It is okay to go directly from the 1 minus 60 over 260 statement to a decimal answer by using your calculator. You are not required to do that fraction subtraction. You can go straight from this statement to a decimal answer. Okay, part C. An adult book or a children's nonfiction. And we learned in a previous video, when we see that word or, that means add. So we're using our addition rule, and we know adult or children's nonfiction should be P adult plus P children's nonfiction minus the overlap. Well, if we look at this table, here's my adult column, here is my children's nonfiction. There's nothing in common between the adult column and the children's column. So that overlap should be 0. So this just becomes P adult plus P children. We would say that these two events are mutually exclusive. These we can calculate from the table. Adult should be 100 over 160. And children's nonfiction is going to be that 60 over 260. And we add those numerators, we get 160 over 260, or 0.6154. Okay, let's try another one. Before we do, you're going to notice that there are a lot of probability questions that depend on a deck of cards. I don't expect that you have that memorized. If you're not big on playing card games, that's fine. I will post this picture with any question on your test that requires knowledge of a deck of cards. So all you need to do is refer to this picture. To clarify, first row is hearts, second row is diamonds, third row is spades, and fourth row is clubs, and we call those the suits. There are 4 suits in a deck of 52 cards. Okay, for our second example, it says if one card is drawn from an ordinary deck of cards, find the probability of getting each event. A 7, an 8, or a 9, a spade, a queen, or a king, a club or a face card, an ace or a diamond or a heart, a 9 or a 10 or a spade or a club. So before we tackle this, we can already see this is going to challenge us a little bit. We've seen questions where we have A or B, and questions where we've had A and B. We haven't had issues where we've got A, B, C, or A, B, C, D. So we're going to have to take what we know about addition and multiplication rules, and we're going to have to extend those a little bit to more complicated probabilities. Okay, so let's go ahead and start with A, the probability of finding a 7 or an 8 or a 9. Because we're using a problem with the word or in it, we want to use the addition rule. And in this case, we're dealing with situations than more than 2. So I'm going to sum that up in words. The addition rule basically says add up the individual probabilities, words are hard, and then subtract off any double counts. Subtract off any overlap. So we're going to look at each of these, starting with A. We're going to add up the individual probabilities and then look if there's any overlap and subtract that double count off. For A, a card in a standard deck of playing cards can't be a 7 and an 8. It's either a 7 or an 8. A card can't be an 8 or a 9. It's either an 8 or a 9. So that means that 7, 8, and 9 are mutually exclusive. So to find this probability, I just need to add the individual pieces. Probability of 7 plus probability of 8 plus probability of 9. Well, there's 4 7s in each deck, 4 8s, and 4 9s. And I know that there's 52 cards in a standard deck of playing cards. So 4 plus 4 plus 4 is 12. This is going to be 12 out of 52, or 0.2308. All right, let's try the next one. At the surface, it looked kind of similar. It says the probability of being a spade or a king or a queen. For these, there is some overlap. I know that there is a king of spades in the deck and that there is a queen of spades in the deck. They can't be a king and a queen. Those two are mutually exclusive. So the only overlap I'm worried about is the king of spades and the queen of spades. So 2 cards are going to be double counted. When I set up my addition rule, I need to subtract off that double count. So spade or king or queen is going to be spade plus king plus queen minus that overlap at the end. So for spade, that's a suit. I know there are 13 cards in each suit. And then there are 4 cards of each type, 4 kings, 4 queens. And then there are 2 cards that got double counted. So 13 plus 4 minus 2 is 19. And 19 out of 52 is 0.3654. I would encourage you, now that you've seen B, to pause this video and try C and D on your own before I go through this work. C, D, and E are going to look very similar to B, where you're analyzing the overlap before you start the probability calculation. Okay, for C, we're looking for club or a face card. For those of you who are not familiar with a standard deck of playing cards, a face card is a jack, king, or queen. Excuse me. So on a standard deck, those are the 3 cards that actually have a picture of a person on them. And in this case, the overlap is going to be those face cards that have a suit of clubs. So the king of clubs, the queen of clubs, and the jack of clubs. So we need to subtract off those 3 double counts. So we're going to end up with club or face card, and face card is king, queen, jack, minus that 3 that we double counted. So we know a suit is 13. Each of the face cards has 4 in a deck, and then we're subtracting off those 3 that got double counted, the king, queen, and jack of clubs. And I got 22 out of 52, which is 0.4231. Okay, I'm hoping this is starting to feel a little bit more familiar. Let's try 2 more. For D, it's ace or diamond or heart. So ace, we know there's 4 aces in a deck, and then a diamond and a heart are 2 suits, so 13 and 13. And there's 2 overlaps. There's an ace of diamonds and an ace of hearts. So the probability of ace or diamond or heart is ace plus diamond plus heart minus that overlap. So 4 plus 13 plus 13 minus 2 is going to give us 28 over 52, which is 0.5385. Okay, for E, a 9 or a 10 or a spade or a club. Sounds scary? Same process as the last few. Start by looking for that overlap. We know 9 and 10 don't overlap. You're either or. We know spade and club don't overlap. You're either a spade or a club, not both. But there are a 9 and 10 of spades, and there are a 9 and 10 of clubs. So in this case, there are 4 cards that get double counted, the 9 and 10 of spades and the 9 and 10 of clubs. So we're going to split this into 4 separates, 9 plus 10 plus spade plus club, minus that 4 double count. So there are 4 9s, 4 10s, 13 spades, and 13 clubs. So 4 plus 4 plus 13 plus 13 minus 4 is going to be 30 out of 52, or 0.5769. Okay, one more. Similar idea. We're starting with playing cards. And this one says 4 cards are drawn from a standard deck without replacement. Find these probabilities. All cards are jacks. All cards are black cards. All cards are hearts. So these problems involve and, even though they don't say and. If I want to say all cards are jacks and I'm drawing 4 cards, that means a jack and a jack and a jack and a jack. So sometimes these and problems are stealthy and you have to think about how you would write that word statement out. And if you have to use and to explain it, it's a multiplication rule problem. We also have to remember that without replacement means that these events are dependent. We're going to need to use conditional probabilities for the second, third, and fourth card draw, because when we take that first card out, we don't put it back. So our second draw is from fewer cards. Our third draw is from even fewer cards. So starting with A, all cards are jacks means jack and jack and jack and jack. And the multiplication rule says first one times second one given first one. And then we're going to extend that times the third one given the first 2 times the fourth one given the first 3. And it looks a little complicated when written that way, but I think that you guys have the idea down because we've seen something similar with that bag of marbles in a previous video. So the probability of getting a jack with a fresh deck of cards, is 4 out of 52, 4 jacks in the deck. For that second draw, I know that I've removed one of the jacks. There's only 3 jacks left and 51 cards. For my third draw, I know I've removed 2 jacks from the deck and 2 cards from the deck. So 2 out of 50. And that pattern continues. By the time I get to that last jack, I've removed 3. There's only 1 left out of 49 cards. So in symbols, it looks intimidating. In numbers, we can see a pattern. Because we're removing a jack and then another jack and then another jack, both the numerator and the denominator are decreasing by 1. We're removing 1 jack and 1 card. If you plug that into your calculator all at once, it's going to give you an ugly decimal. So what I did is I multiplied the numerators and the denominators separately, and I got 24 over 6,497,400. So the number of 4 card hands that we can draw without replacement is 6,497,400. That's a lot of possible 4 card hands. And 4 jacks represents only 24 of those 6.5 million options. If you do that division, you're going to get something funny on your calculator. It's probably going to say 3.6 something 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 e to the negative 6. That's your calculator's way of doing scientific notation, and it means it's a really tiny decimal. In that particular instance, I'd encourage you to leave it as an ugly fraction. That ugly fraction is going to be easier to interpret than super tiny decimal. Also remember, do not round those super tiny decimals to 0. Getting 4 jacks is possible. It's just very unlikely. Okay, I'd encourage you to pause the video again, try B and C on your own. I'm going to come back in just a minute and go through those answers really quick. Okay, for all black cards, same idea. We need to use that conditional probability. The difference here is there are more black cards in the deck than there are jacks. Half the deck is black and half is red. So of those 52 cards, 26 of them are black in a fresh deck. So that first probability is going to be 26 out of 52. And then as we remove black cards from the deck, both the numerator and denominator are going to go down by 1. If we multiply the numerators and denominators separately, I got 358,800 divided by 6,497,400. That gives a slightly less scary decimal answer, 0.05522, or about 5.5%. For the last one, similar idea. All cards are hearts. The difference here is we're looking at a suit, hearts, and we know that a suit has 13 cards. So that first pH is going to be 13 out of 52. And just like the last few, that numerator and denominator are both going to decrease by 1 as we remove hearts from the deck. When I multiplied those, I ended up with 17,160 over that 6.5 million, which is 0.002641. So less than 1%. Okay, if you have any questions on the examples that you've seen or on how to calculate probability for simple and complex events, feel free to email me, send me a text message, or contact me during office hours. Otherwise, I'll see you in the next video.